Good afternoon, Professor.
Good afternoon, Christopher. All right. Now we're going. Good afternoon, Valentina. Good afternoon, Michaela. Now we're rolling. Good afternoon, Dante. And I know I skipped someone because it's before. Good afternoon. Oh, that was a hello. That cat. I think that was Bree. Like a voice.
Good afternoon.
Good afternoon. I think that was Allison. That was a voice. I'm loving it. Oh, wait, and there's someone else here. And I skipped someone. I know I said Valentina, Michaela. I think I skipped Michaela. And I think I see her avatar. Good afternoon. And Samantha Davis. Good afternoon, Dante. Good afternoon, Christina. Good afternoon, James. Good afternoon, Key. Good afternoon. Good afternoon, Samantha. Good afternoon, Juliana. Good afternoon, Brad Lee. And wait, who am I? I skipped someone. But yes, thank you for saying good afternoon. Who did I? Okay, I think my good afternoon, Yaverboard. James, if I didn't say good afternoon or hello. Okay, let's get this party started. Yes, let's get this. Let's just literally get this. Okay, we're gonna get straight to it. You can try to remind me. We'll try to take a quick break today because I know we didn't have one yesterday. We'll try. You can remind me about halfway through. I mean, it can't be a long break, but if you remind me, whatever, about 5 o'clock, that doesn't mean I'll do it right at that second, but it can remind me to wrap up whatever I'm doing for a moment so we can take a quick break. Also, I don't know if you know, I've been thinking that hi, Dennis. Okay, hello, awesome. I've been thinking that the class ended at 6:45, and I think I'm trying to let you, but I think the class ends at 6:55. I'm just saying, and you could correct me if I'm wrong in the chat, but I actually think the class actually goes to 6:55. And I think I've been cutting it short, which I guess is sort of compensation for the fact that we really haven't had a break. But so we will try to have a break today, but I think 60, tell me if I'm wrong, but I think we actually go to 6:55, which makes sense when you do the math. Is it? Wait, but
it's 6:45.
Oh,
You're not right. You're wrong. I'm just messing with you. It's 6:45 though.
But okay, wait. So, and I believe you, but something doesn't make sense then because then that's
So the first session is from 4:05 to 5:45. Then we're supposed to have a 10-minute break, 10-minute break to 5:55, which when the next session start until 6:45.
Oh yeah, no, you're totally right. I'm sorry. Yeah. Oh, you are right. Yeah. Okay, sorry. Oh, and hello, Teskeen. Sorry. Okay, no, yes, that does make sense. Okay, so it is 6:40. You're right. Okay. No, you're right. 2 hours and 40 minutes. You're right. You're both right. That does make sense. Okay, so then I'm glad we just clarified again. Okay, so it is 6:45. But yeah, and yes, the math right. And if it says that in CUNY first, also then yes. Okay. So, but that's what we've been doing. So then I'm doubly crazy. So yes, okay. So, but I should be trying to give you a break. Oh, hello. Oh, sorry. And hello, direct chat. And hello, Mario. Okay. So sorry. So ignore that. Yes, 6:45. But yes, if you remind me, I'll try to give you a quick break today. I mean, that would be the human thing to do. What is Mario? Wait, what is that, Mario? Oh, yeah, what is it? Whoa. It's so weird because recently my 11-year-old my 11-year-old nephew was showing my 8-year-old like a YouTube where they had an ape actually play Minecraft, a $40,000 research project. And of course, the ape was better at Minecraft than like I am. I mean, he was like better with redstone, whatever. Okay. It's you. Okay, that's funny. Okay. So let's get rolling though. So we're gonna just try to like be blasting through more of now homework. We're trying to lay out basically the thing that is on the screen right now. Like you may have noticed every day we try to put the equations on that look partly familiar. They're partly a touch off from what happened yesterday, but partly a coming attraction of where we're trying to go. Like the context here ultimately is simple harmonic. Hello, Charday. Oh, sorry. Hello, anybody who joined us recently. Sorry. Hello. Also, I'm a little bit behind now. If you've turned in something recently and have not gotten it back yet, that doesn't mean I don't see it. It means I just fell behind last night. Also, if you got a 27 or something like that on the math methods homework too, but you didn't get any comments, that means I'm totally acknowledging and thanking you for getting in and on time. You've already gotten at least 27 out of the 35 points just for getting in and on time. that all that means, it means I still will look at it more closely to give more feedback and to give more points. Or if you know in your heart of hearts that you just turned in something and you didn't finish it yet, or whatever, and you know in your heart of hearts you probably didn't get much more than 27 out of 35 of it, then just keep turning in things to me as you all understand. But basically, if you got a 27 or thereabouts, that's me saying to you, great, thank you, I see it, it's in, you're on target, but I have more points to give you probably, and you might still have more work to give me, but maybe not. You can send me a private note if you're like, no, mine was perfect, I did everything, I'm just waiting for more feedback and more points from you, Yaverbaum. That's fine. You can send me such a note. Like a tag, whatever. Hold on, let me just a couple other just announcements. Oh, okay. All right, cool. But yeah, what we want to go to today, finally yesterday, I feel in my heart, which I trust more than my brain sometimes, I feel that we technically did finish the very last question of homework 1, question 9. Like, we went through a whole big discussion, a whole big conjecture and verification of how to solve the differential equation that suddenly physics put in front of us. We put together a good guess for a solution to it. Then we verified that solution to it. Then we plugged in numbers and we got an answer. Right. So technically, technically we finished the question. And in many ways, it probably took us way longer to finish the question than some of you would like, right? On the other hand, we said a lot about it. And it's really that last question is like the whole topic of this midterm that you're about to take and that we'll address more explicitly shortly. So what I want to say is, even if certain parts of what we did, went over your head, or you were already bored by that time and you could only pay so much attention, or they went too fast, or blah, 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 blah. We're going to be revisiting all those concepts in all the exercises that we now go on to, like in homework 2 and homework 3, both of which we'll get to today. We won't do all of homework 2. We'll do key exercises in homework 2 that will help you for the exam. And then we will, at the break, when you in the middle of the class, when you remind me, like, it's pause time now, what we'll probably do is wrap up whatever exercise we're in the middle of homework 2. We'll take a quick break, and then probably wherever we are in homework 2, more or less, probably, I'll just shift gears and walk you through homework 3 to show you how it is, like, a summary of the takeaway of everything that's captured by question 9 of homework 1B. So this is, as usual, too long a way of saying there's a lot going on in homework 1B. It's like our initial foray into the whole topic that is this midterm exam. We're going to continue to unpack the details of that question, of the last question of homework 1. Even if you don't feel like you totally get it, we're going to continue to unpack those details throughout all these next exercises in homework 2 and homework 3. So it's all captured, really, everything we're going to say is sort of captured by what's on the board right here, right now. In fact, I'll quickly say something about it. So we're going to homework 2 in a moment, okay? In a moment, after a couple more announcements, we're going to open up homework 2 and do those exercises. Hopefully you'll see a deep similarity to some things we did yesterday. But what's on the board right now, I want you to notice right away, the first 2 equations, the if-then that's on the board right now, they're very similar to what I wrote on the board yesterday. Very similar, but not identical, right? One thing you'll notice is that they are like the equations I wrote yesterday, except that instead of x's, here I'm writing z's. Okay, just to alert you why I'm doing that. That's not a typo. It's an evolution. One thing I want you to see now that we're going to go into homework 2 is I want you to see that anything we did yesterday, like deliberately, the beginning of this course deliberately started with a particular example of a particular physical mass on a physical spring, like on a physical table, that even though it's fictional, it's picturable, and it's very similar to something that you actually really did in a physical actual lab, in the same week. So the idea is that we started with a physical scenario that could have actual specific measurements and numbers associated with it. And we asked a question about a physical, literal, actual, possible specific scenario, and we're like, hey, given this mass on this spring with these details, where would it be once the clock strikes 1, right? Like that's what we were asking. And then it led us to do all this abstract math for like days. Well, at least a full day. All this abstract math, like setting up F equals MA, setting up F equals negative KX, realizing we have a differential equation in front of us, then talking about how to deal with the differential equation in general, doing all this stuff, blah, 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 blah. And then finally we got an answer. And the answer to that specific question was 0.116 meters or something like that, right? And everything we were dealing with there was not only specific numbers, well, not only the example of specific numbers, but it was specifically horizontal displacement of specifically a Hooke's law spring, right? So specifically what we were looking at, grinding that problem, was we were looking for an X function of T. We were solving for X, by which we specifically meant horizontal displacement, like displacement along an X-axis, right? What we want to now realize is that the math that we had to do that was just general math. It's true in general. It could be true of any variable that's behaving the way our X variable was behaving yesterday. So the first thing I want you to realize as we're going through the math today, when we're going to step back and generalize and say, what have we discovered about the mathematical relationship in general through our work yesterday? Whatever we've discovered would be true. I mean, this is the thing of math. This is the good and the bad and the ugly of math is just universally true. Whenever you get it at all, you're getting something that's true throughout the entire universe, not just of any one specific example. So whatever we learned about X yesterday is not especially tied to any physical meaning of X. It would be true of any dependent variable, particularly any variable that depends on time, right? So the first thing I want you to realize here on the board right here is that we're going to take that conclusion that whatever conclusions we came to yesterday about X, and we're going to say, you know what? It doesn't, as long as it's any variable that depends on time, whatever we learned yesterday is true. So from here on in, and you may want to make a quick note of this, when I say Z from now on in this class, like maybe I mean displacement along a Z-axis, but probably not. In general, when I say Z, Z stands for any generalized, arbitrary, dependent variable. That could mean displacement along the X-axis. It could mean, like your pendulum in the lab on your second day, it could mean angular displacement along a theta. Like Z could stand for theta, in other words. Or Z could stand for magnitude of electric field, which it will next in this class, right? Z can stand for any measurement that could depend on time. If you can describe Z with that differential equation that we found yesterday, if you can describe Z by saying its second time derivative is directly proportional to itself, then Z is oscillating cosinusoidally in time. That's what we're really saying according to like the function. According to the function that we conjectured and verified yesterday. Okay, I should go on. I'm going to go on to homework 2. But there are some other details, as you see on this board, that are a little bit different from yesterday. There's an extra little term in the cosine parentheses for sure that you didn't see yesterday. We're going to introduce that today. And then there's this last line, omega doesn't equal function of Z naught. We didn't say anything about that yesterday. That's a foreshadow of something we're going to say today. So stay tuned. Okay, that's enough babbling already. Let me get to homework 2. Oh, wait, saved by the bell, someone's here. Okay, I'm going to turn our attention to 2. Hold on, bear with me for a second. Obviously, you could still, you could still stop me at any time. You can always stop me at any time. But I got to stop myself first. All right, so homework 2. And again, well, okay, I am going to say, well, see, God, so nonlinear. How many ADHD physics professors does it take to screw in a light bulb? A fish. Okay. And I'm sorry, that joke is probably offensive to fish. I'm sorry. The one thing I do want to say before I forget, so we're going to go to homework 2, mathematical methods. I'm writing this down to force myself not to go off topic. I'm going to pull it up in a second. But before I forget, of course, I do want to address more details about the exam by the end of today. Hopefully I'll do it in a little more detail, but I'm going to say right now, just in case I forget, I've been saying I'm going to give you a practice exam that I'm going to make, and I'm going to make available to you a practice exam that you're going to come into lab tomorrow. First, you're each going to try it by yourself for practice, right? I know I've said this, but hear me again. And you could be open universe. You can open your computers. I hope you do. You can look at old notes, but do it for the first hour and 15 minutes, whatever Professor O'Talley says, do it by yourself first so you can really find out what your deal is. And then just know that after about an hour and 15 minutes, she'll say stop, but she's not collecting anything or anything like that. It's for your own good. It hurts me more than it hurts you. Then for another an hour and 15 minutes, then you could totally all work together and help each other. And I would totally suggest, and that also means, by the way, when you go to work by yourself, I would highly suggest you go out of order on the exam. Like if you don't like question 1, skip to question 3 or whatever, especially thinking in the back of your mind, okay, cool. If I skip to question 3, that'll be good because like my partners next to me are going to be doing question 1. So then we can trade stuff afterwards. You could even make that arrangement right when you start. I don't care, but just force yourself to work by yourself first and then help each other. Otherwise your help is not that helpful. I'm saying all this to say, see, God, so not. I'm saying all this to say that I checked right before class. The exam that was already put in your Google Classroom that's labeled midterm exam from last semester, from spring of 23, actually that is more even appropriate and relevant and correct than I expected. Like we actually had covered just about the same amount of material there then than we have now. So I could tell you right now that the practice exam I post, if it's not literally that, if I don't just literally change the label down and say, yep, this is your practice exam, people go for it. If I post something, if I don't literally post that, it's just going to be a slight variation on that. You can trust, I'm telling you right now, in case I forget, you can trust that exam that's already in your Google Classroom pretty much is your practice exam that you're going to do tomorrow. Have at it, early if you want. You can start looking at it tonight. And also you can therefore trust that that's very similar to what your actual exam will be. Not identical, but very similar. We'll change things wherever we literally give you answers, but wherever we literally don't literally give you answers, you can assume we won't change things and you just have like extra research time to do it. So I've checked, you can trust that document is a very good indicator of basically what you'll be doing in lab tomorrow and then what you'll be doing at home from Thursday to Sunday. Okay. I hope, actually, I'm going to start homework 2 now, which is all. Can you raise your hand if you just heard me say that about the exam and if that's clear? And can you raise your electronic hand? Cool. Awesome. Thank you, Bree. Thank you, Samantha. Thank you, James. Thank you, Michaela. Thank you, Allison. Thank you, Valentina. Thank you, Keith. Thank you, Juliana. Thank you, Bradley. Thank you, Christina. Thank you, Dennis. Awesome. Thank you, Toby. But thank you. Oh, cool. Okay. Wait. Okay. Thank you. Awesome. And if I didn't mention your name, it's just because I just did. But cool. Thank you. And you can put your hands up. No, wait. I'm looking in the chat before. Well, wait. So what I'm saying is, to opinion and everybody, the practice questions to review for the exam is that exam that's posted in Google Classroom right now. I might post a slightly different version of it to call it the practice exam, but that is your practice for the exam. Those are the practice questions, and they don't count. They're practice because they don't count for a grade. They're for practice, but they are incredibly similar to the real thing. So those are the practice, and those practice you'll find that practice exam or the exam that's posted already in Google Classroom, you'll find that those practice problems are, once you get used to all this, you'll see they're just expanded versions. Well, at least the first 3 problems are expanded versions of any of these homeworks that we've done, 1, 2, and 3, and or anything you did in the lab, particularly lab 1 and 2. Okay, the very last question gets into lab 3, and we'll get into it by the end of today or tomorrow. The very last question is the stuff you haven't seen yet from me, but this course goes fast. We have 2.5 hours today. We have 2.5 hours tomorrow. So I'll get to that. But it goes in order, So the very last question you may only sort of understand from lab right now, but other than that, it's all. So wait, I want to make sure, Penina, did I just answer your question in the chat? Could you just let me know if it's clear that the practice questions are the exam that's posted under exams in Google Classroom, the exam that says the midterm one from spring of 2023, that's your practice questions for the exam, plus homeworks 1, 2, and 3. But I'm going to pause for a second. Opinion, is that clear?
Oh, she ain't in here.
Maybe. Okay. Thank you. All right. Well, could anybody, Christopher or anyone, could you just verify if it looks like I've answered? Do you feel that I've answered, Panina? Because that's an important, I don't want there to be any confusion on that. Does anybody feel that I've answered the question that Panina's posed? Yeah, okay. Thank you, Key. And thank you, Michaela. Okay. Okay. Thank you, Samantha. Thank you, Alana. Okay. I just want to, okay. All right. All right. Thank you. And all of you. And again, every single one of you just said yes. There's about 3 different portals you could submit for points for that. You might think it's silly. I don't think it's silly. Either way, you get the points, whether you think it's silly or not. It's not a race. Doesn't matter if you were the first one in the chat or not. All right, cool. So that includes Dante, for example. Okay. And Allison and Juliana and Alana and Samantha and Michaela and Key. Okay. And Dennis. Yeet. Okay. I love the word yeet. Okay, that is definitely a gift from your generation, the word yeet. Okay, that's awesome. And I don't mean the artist. I mean, he's good too, I suppose. But all right. Okay, so, I mean, the musical art. All right, so let's do this homework too. Let's get this party started. Okay. Let me just open it. Excuse me. Okay, here we are. Here we are. Okay. Right, derivatives. Okay. I'm gonna do the 5-step method just for this first one. I know I'm gonna do the 5-step method very quickly right here to get us rolling, but then from then on in, I'm gonna, hopefully be a little bit faster about it. So here, in other words, from here on in, I may sometimes just give answers, not full solutions. It's not always a guide to what you should be doing for full points, but first it is. I know I mentioned this. Okay. Okay, everything I just wrote here. So I'm doing A of 1 of homework 2. I believe that everything I just wrote was some kind of version of step 1 diagram and fact pattern, right? I believe I mentioned this a couple days ago. Here's my you notice there's no diagram given in the homework. It just looks like raw math. Well, to me, all the more reason I better provide a diagram. That's totally true of your exam. Whether or not the exam provides a diagram, you provide a diagram. So here's my diagram. It's a cosine function, right? Because what's given to me, here's my diagram and fact pattern. What's given as a fact is that we have a cosine function, x equals a cosine omega t. Now, that means a couple of things, like that function, x equals a cosine omega t. Lowercase t is clearly what is the independent variable, because I'm doing something to it. X, it's the input, right? X is the output. It's the dependent variable. So I set up a graph where x is the vertical axis, t is the horizontal axis, right? And it's a cosine function. So, okay, so I made a cosine function. Cosine function looks very much like a sine function, except the one big difference between the two, as you all know, but starts to become, I think, very, very handy and relevant in physics, is that sine is super and cosine is crappy. Or put another way, sine is sensible and cosine is counterintuitive. What the heck do I mean by that? I mean that sine of 0 is 0. Sine of 0 is 0. As the angle gets bigger, as theta gets bigger, or in this case, t gets bigger, sine gets bigger. Sine starts at the origin. Like if you were on a desert island making up math, that's the way you'd make up, I think. You would make up a function like that. The input is 0, the output is 0. As the input gets bigger, the output gets bigger. That seems sensible and reasonable and common and first instinctive to me. Whereas cosine does not start at the origin. Like they have the same shape, right? But they're one is a translation of the other. Cosine starts with a y-intercept that isn't 0. What's the y-intercept in this case? It's clearly a. because I know that the cosine of 0 is 1. This function says x equals a times the cosine of omega t. So if in other words, I'm saying like this graph I know is right because just according to the function, and I could say this, if you were taking an exam, if I were taking an exam right now, this is my, my diagram and fact pattern. I'm inferring all this from the facts that were given. Note, like if t equals 0, if I just plug into that function that they gave me, x equals a cosine omega t, like I'm not solving anything yet. I don't even know what the question is yet. That's why this is still step 1. But I'm just noting, I'm noting things I understand about cosine. If I plugged in 0 for t into that x equals a cosine omega t, cosine of omega times 0 would be cosine of 0. Cosine of 0 is 1, but then 1 times a is a. So if I plug in 0 for t, I get out a. So a is the y-intercept of this graph. I mean, again, it's like one of those things. It's like obvious once it's obvious, and it's not obvious until it's obvious. So I can label. There's a label a right there in the graph. I'm like, by providing this picture, like, how do I know when I'm done with this picture? I know, or how do I know when it's served its purpose? I know when it's served its purpose when every label in the picture ends up defining one of the terms, the variables or the constants in the problem I have to solve. So there's a label for a, right? And then omega, and clearly there's a label for lowercase t and a lowercase x, like those are the variables. A is a constant, and the other constant that's given in this function is omega. What the heck is omega, or what does it mean? What it means is 2 pi over the span of time between one peak and the next on this cosine function. Please note, I am over talking it as always, but just trying to establish, again, what it would sort of mean to do something like this on an exam. This is all step 1 DFP, but I'm setting my table so that soon I can eat. But please notice this definition of omega, or this understanding of omega in these graphical terms. This is all just math now, right? This is literally by the meaning of how that function is written. I don't even yet have to know anything about a mass going back and forth on a spring to understand that what omega is the number of cycles per unit time. And a cycle in pure math or on a graph like this is measured in radians. There's 2 pi radians in one cycle. Okay, so all of this is my setup before I do anything. Then step 2, like, what is the question? And more people lose more. Just please never skip this step. Just always make it clear, especially because, again, for some of you who are still getting this, you're going to do this whole exam on blank white sheets of paper. You're not going to write on the question sheets, and you're not going to copy and paste the questions. It's part of your job to understand the questions enough to be able to rewrite them, to distill them into your words. I promise, I cannot emphasize enough that little kindergarten moments like that, where you have to like rewrite the question, actually are like the essence of research science. Anyway, so what is the question here? What is the question? I don't even remember. What is the question? Oh, the question is, if given, that function, the first question, lowercase I believe, was what is the first derivative of that function? I do believe that's the question. Stop me if I'm wrong. Yeah, it is. Okay. Right. So that's the question. What's the derivative of that function? Notice this is a purely mathematical question. I mean, in my heart, if I understand physics, I know what they're really asking for is what's the velocity of this object? What's a function that describes the velocity of this object, like how fast it's going at any moment? If the original given function is describing where it is at any moment, what's being asked of me now is how fast is it going at any moment? But I don't even have to care in order to answer this. I'm going to go to step 3. GDP. General definitions and principles, right? Now, again, someone asked me a really good question after class yesterday. Like, I mean, I'm going to use my words, not theirs, but they were like, wait, so they were just asking me to get straight, like, what's the deal with step 1? Like, what is, sorry. Yes, absolutely. I'm sorry. Yes. Tell me what, someone in direct chat just asked me to go back. and they asked in direct chat. So I'm not going to say that person's name, but I'm going to say, I love it when people ask me to go. Only someone who actually cares and is paying attention would ask me to go back. So remember, there's a portal for that. You can submit for points for the mere fact that you just asked me to go back. And then they just said, thank you so much. So that you could submit also points for closing a conversational path, because now I can go on. That's awesome. Seriously, direct chat person, you know who you are. I appreciate it. Okay. Okay, so now I'm going to go forward. And yeah, just notice now in step 3, like step 1, again, when I was in, I know that you've all heard a million times in 7th grade, like write down first what you know, and then solve for what you don't know. Yes, like that's right. Like we learned it in 7th grade for a reason. But what they never told me in 7th grade, what it took me till I was like 35 years old to realize is, oh, wait, there's 2 different kinds of things that I know. There's some things I know because the problem told me, and then there's some kind of things I know before I read the problem that I'm going to need to pull out of my brain to use in this problem. Those are totally different types of knowledge. Generally speaking, the second type happens to be triple equal signs generally, and the other type happens to be double equal signs. Step 1 is whatever the problem told you. Step 3 is now, what can I bring to bear on this problem? Well, now here I'm going to do something a little bit slower than I did yesterday. Like for those of you who are still with me, you'll notice that really what this question is asking us to do, it's literally asking us to go backwards on what we did yesterday, right? It's asking us to do what we did quickly in the last 15 minutes of yesterday. That is, yesterday we were given a differential equation and we had to come up with a solution for it. Here what's happening is they're just providing, I am just providing us with a function, and I'm asking us to differentiate it. So what's really happening here is I'm providing us with something that possibly could be a solution to something. I'm not calling it that, but I'm just like, here's a function. Here's a dependent variable related to an independent variable. Now, could you take a couple of derivatives, and just see what happens? So what I'm really asking you to do now is take a function that might actually be the solution to a differential equation, and I'm asking you to run the test, right? We're just going forwards now on the thing we're just doing what we did at the end of yesterday. So let's take these derivatives a little slow because everybody's at different stages with derivatives in this class. I mean, in theory, we've all done a million of them. But so step 3 GDP, the first thing I'm going to say is, well, I'll even say in general, just to be clear, I'm saying in general, if y equals cosine of x, then dy dx equals negative sine of x, right? Notice I just changed to y and x. The problem is about x and t because really it's a physics problem. It's about position and time. But I just shifted gears on purpose to good old y and x because I'm trying to make the point that I'm just talking about what you would say in a math class, like before all this. I'm just saying if we have some function y is a cosine of x, then it is in general, then it is true that the derivative of y with respect to x is negative sine of x. Now, if you want to be, I mean, like that's a thing that I think is known. I think it makes sense too. And I think, by the way, depending on who you are and where you are in this class, that's a moment right there where, like, if you actually get that, if you get that if you walked up and down a cosine function, asking yourself what's the slope at any given point that you're looking at in a cosine function, like, and you made a graph of all the slopes, you would realize, it's not a surprise, you would get a sine function, but flipped upside down. Like if you really think about it, it actually makes sense. And you really could, with a picture or for a few English words, you could actually argue and show that you understand this in your exam when this comes up, and it will come up. Right? I'm going to say that slightly slower. And you might, and maybe one way to show that you basically understand this, and I'm on purpose, I'm not writing this down now. For those of you who are like really paying attention, I'm saying, picture a sine graph for a minute. Picture a sine graph. Starts at 0, 0, right? When if I'm talking about y equals sine of x, right? When x is 0, y is 0. At 0, 0, the value of the graph, The value of the graph is 0, right? But look at it, just picture a sine graph in your mind. Picture a sine graph in your mind. That point at the origin, if you asked yourself what the slope is doing there, the slope is clearly pointing up, right? The graph is rising at that point, and it's rising pretty steeply. Like right there, the graph almost looks like a straight line, like it's shooting up, right? Which is why for small angles, y equals sine of x is approximately identical to y equals x, right? If you think about right there, the slope is high. The slope, that graph right there is almost a y equals x graph. The slope is pretty much 1 right there. Then you start going up and up. The values of the sine are getting higher and higher. But what's happening to the slope of the graph? It's getting less and less slopey, right? It's getting less and less steep, all the way to where you get to the top. I'm talking about a sine graph now. For anybody who's still listening, I'm on purpose sidebar. I'm talking about a sine graph so you can picture something. When you get to the top of the sine graph, the highest possible value, when the sine, when you're at like pi over 2 radians, when you're at 90 degrees, the sine is 1, right? It's the highest possible value. You're at the top of the mountain of the sine graph. Well, what's the slope doing? Well, the slope is flat because you're at the top of the mountain. You've been going up. Now you're about to go down. If you were a ball, your velocities were like getting less and less positive. They're about to get more and more negative. At the top, your slope is 0, right? So when the value of sine went from 0 to 1, the slope went from 1 to 0, right? And then you start coming down. So the values start going down, but the slopes are getting increasingly negative. Now you're coming down, right? So the slopes are negative, but they're getting steeper and steeper. And someone's calling me, oh, okay. You're getting steeper and steeper until you, and I'm about to finish this. If you get my point, I think you get it already. And if you don't, you don't. But what I'm just trying to say is if you picture a sine graph, the values are going up and down, right? From 0 to 1 to 0 to -1 to 0. If you look at what the slopes are doing, the slopes are also going up and down, only, transposed. Like when the value is really high, the slope is 0. When the value is 0, the slope is either really high or it's really negatively high, right? So it makes sense. And it's just like what we were saying in question 8 of the homework the other day. Like as you go back and forth, your velocities are going back and forth. And as your velocities are going back and forth, your accelerations are going back and forth, right? Each one, the derivative of it is doing like the same thing as it's doing, but with a negative sign or something like that. So it's not just a memorizer. It's not just black magic to say that the derivative of sine is cosine. We're saying that the slopes flop around back and forth of the sine graph, just like the actual values do, only shifted over. And okay, so if you really, again, I said all that. Maybe it's too much for some people, and that's fine for the moment. Maybe it helped you understand a little bit. But for those of you who are like, if you're looking for ways to really show me on the exam that you're really in it to win it with this material and you really get it, and that's a kind of thing you would add on your exam right now. You would make a little diagram or a little English showing that you understand why this thing is true that I just wrote down, or at least why it's reasonable. Okay. But for the moment, I'm writing it down. Anyway, hold on 1 second. I'm going to pause for one. Okay. 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 So, all right. So you say that, but on the other hand too, if you're asking, wait, but is it sufficient? Wait, am I allowed to just like write that on the exam? You write something like that. Yeah. But try to give a quick, show that you know what it means at least. But yes. Okay. So you write that. So that's a GDP, but here's another GDP now. But hopefully you all understand. Oh, that my board just went bananas. Hold on. Sorry. Yep. Okay. The universe just broke. Hang on. Okay. But you certainly have to write something like that. That's a GDP we're going to use, but we're also going to use the following. I think I've written this. Have I written this before? I'm not sure. If y equals a function of x and Z equals a function of Y. Now check this out. I'm changing the view again. This blows my mind every time. Many of you know something about what I'm about to say, but many of you have maybe never seen it written this way before or never thought about it this way. Then also I'll just show you. Okay, the thing that I just wrote down in my notation is what's known as the chain rule, right? What I'm saying is, I mean, the chain rule is the thing that you apply. And again, in principle, everybody knows this. And I know that in principle, everybody knows this, but also in reality, we're at different levels with it. And like anything else, many of us think we know it, and we do know because we've used it. But maybe we just, like many other things in math, we just like memorized it and accepted it and moved on with it. I'm here to plead with you to understand nothing in math is actually just a memorizer. It feels that way when math goes as fast as it does in high school and college. But actually, all of math, I promise, is actually meant to make sense. And as long as you ever have time to break it down, nothing in math is just out of nowhere. That's why it's math. So the chain rule that you might have just memorized, some of you might have just memorized. What I'm saying, the chain rule is, if you have a function of a function, right? So if you have y is a function of x, where x is the input and it spits out y as the output. But then if you have z as a function of y, right? So we put a number in a box and called an input, and out comes this other number called y. Then we take that number, we put in another box, and out comes this new number called z. So if we have that situation where we have a function of a function, then we have this thing called the chain rule that says, if you want the derivative of the whole shebang, if you want the rate at which the outermost number changes in response to the innermost number, then what you can do is take the rate of change of the outer to the middle and multiply that by the rate of change of the middle to the inner. And what you will get, so as they say in math, like to do the chain rule, what you do is you take the derivative of the whole thing and you multiply it by the derivative of the inside, right? That's what many of us have memorized. I'm here to say, if you think of notation, if you take notation seriously, it actually makes total sense. The derivative of z with respect to x equals the derivative of z with respect to y times the derivative of y with respect to x. The dy's cancel. To me, it's like, oh, right. Oh, I see that. Now you might be saying, wait, are you always allowed to cancel? I didn't know you could treat derivatives like fractions. Derivatives are fractions, and it's really important to view, or at least their ratios. A derivative is a slope taken to the limit, right? A derivative is a rise per run. Only that's all it is, except for this catch that it's taken in the limiting case where the run is arbitrarily close to zero. But that's what a limit, in fact, I'm even gonna write that. You could even write this somewhere as a GDP if you want. No, what is, when we write dy dx, the reason that's how we write derivative is not so to be annoying. It's because what it is I'm going to do this quickly. I will get back to the topic, I promise. But again, if at least one person out there suddenly benefits from this, it's worth it. And there will be at least two of you that will think you're not benefiting about this, but then like 5 years later, it'll turn out it was. Like this last thing that I just wrote, like used to, right? You've all seen this last thing that I just wrote, the definition of the derivative. Okay, every time I saw that last definition, especially in the first calculus class, I wanted to puke. I mean, it didn't mean anything to me, and I had to memorize it and do proofs with it and blah, blah, blah. It just was a bunch of gobbledygook, and it made me hate derivatives for a long, like I wasn't interested. But look, go backwards. All that thing is saying, this big complicated looking thing, it's saying that f of x plus delta x minus f of x, that's just a way of saying y2 minus y1, right? Because y is a function of x. It's just saying if delta x is the run between 2 points, like if you have 2 points, x1 comma y1 and x2 comma y2, the difference between the x values is delta x, right? So delta x just means the run between 2 points. So when you plug in the first x, you get out some y, and then you plug in the other x, i.e. x plus delta x, you get a different y. So all this gobbledygook is just saying that what a derivative is a slope. It's a change in y values divided by a change in x values, but taken to the limit, taken in the arbitrary case, in the infinitesimally small case where the difference between the two x values is so small that it's as close as it can possibly be to 0 without actually being 0. Now, of course, that's a whole discussion in itself, which I might or may not get into, but of what limits are, right? But in short, a limit is, I will get into that, but a limit in a science class is actually much easier to picture than a math class. When I say the limit as delta x approaches 0, which I know, again, is a big turnoff to all of us. And the minute we do limits in math, especially every time they say, at least to me, every time in a math class, they used to say, it's as close as you can get to 0 without actually being at 0. In my head, I was like, well, this is as close as you could possibly sound like talking math without sounding like math at all. Like that is just hard enough to sound like math to me, but just nonsensical enough and insane enough to be like, where'd my math go? What are you talking about? As close as you can be to 0 without actually being 0. Like, are you 0 or are you not? Right? Believe me, I used to have that problem. And everybody does. That's why it took thousands of years to actually formalize this concept. But you know what it means? You know what limit as delta x approaches 0 really means? It means so small that we can't measure it, but big enough that we know there's a measurement to be made. That's what it means. Or let me put it even better. It means big enough to be there, to be registering on our measuring equipment, but too small to show a number on our measuring equipment. That's what it means. It means there, but immeasurably small. It means below the threshold of measurement. And if you're a scientist, the only kind of numbers that you can believe are measured numbers. So if there's a blip on the screen and it's blipping on the screen, but you can't, but any micrometer or any meter stick or anything or any electron microscope you have is not small enough to see how small that blip is, but you see a blip on the screen. That's a limit. It's there, but it's immeasurably small, right? It's got a quantity, but we can't quantify it. Put another way, we can't distinguish its size from any other blip on the screen. That's what we mean by limit. Like really. So I'm like a little off the topic of it, but not really. But I'm saying a derivative is just a slope in the limit as run gets arbitrarily close to 0. So a derivative is a ratio. That's why we write it as dy over dx. We just mean delta y over delta x in the really small case. So it is a ratio, and normally you can treat it as a ratio. It's just that it is a ratio of infinitely small quantities. So sometimes we really have to be careful about separating those quantities, sometimes, but not always. So anyway, the chain rule is just taking advantage of that fact and saying, okay, the outer derivative is called dz, is the rise of z with respect to the run of y. And then dy dx is the rise of y with respect to the run of dx. So of course, if you write it that way, you see the dy's cancel, and that's your full derivative. What does any of this have to do with the problem? What does any of this have to do with actually solving it? Well, now that I've established in my GDP, I've established that if y is the cosine of x, then the derivative is the negative sine of x. But I've also established that if I have a function inside a function, I better take the derivative of the outer and multiply that by the derivative of the inner. And it's called a chain rule because you could do that forever. You could just, you get a function of a function of a function. You could chain them all and do that as many times as you need to. So now that I've established those things, I can go to step 4. Practical application and work. And again, if you're taking an exam, I mean, I would highly recommend that you label your steps like this. I can't take off points if you don't label them, but it's helpful. But one good way to know that I'm now getting to notice when I did step 3, I wrote like in general, blah, 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 blah. And I changed my letters from X and T to Y and X. Well, now that I'm getting like back to reality of the problem and I'm doing step 4, one way to signal that is I can say something like here, here means now in this case, as opposed to in general, here we have X equals A cosine omega t, right? So we can say like y equals, if you like, you could say something like y equals omega t. So we could let y equal omega t. Now I'm dragging this out. I'm not going to drag this out on every single problem, but again, just to show you, number 1, what's really going on here for people that are rusty with calculus. But number 2, for those of you who are not rusty with calculus, I'm giving you like a script for how to blow me away on the exam and show that you really do know your calculus. I'm saying let y equal omega. And again, I know I'm doing more steps on paper than many of you think you're doing in your mind. I know many of you can get to this answer much faster in your mind. But I also want you to know, if you get there much faster in your mind, don't sell yourself short. It means you're doing all these steps really quickly. You have to be. You can't be skipping these steps. You're just doing them really quickly. So good for you. I mean, really good for you. So now give yourself credit and lay them out on the table. So let y equal omega t and x equals a cosine of y, right? That's what we have here, a function of a function. I'm renaming things now. I'm saying the inner function is omega t. The outer function is a cosine of that inner function, right? Thus, like applying the above, we have x equals negative a sine of y, right? I'm taking the derivative of the outer function, x equals negative a sine of y. But since, but since y equals omega t, I have to take the derivative of that. The derivative of that, dy dt equals omega. Now, why is that? You might want to, well, the quick answer is if derivative is slope, y equals omega t is like writing y equals mx plus b, where b is 0. I mean, you could do a sidebar on this if you want. And if y equals mx plus b, the derivative, the slope, is m. Or you could use the power rule if you like. Maybe I should, and you should stop me now, because now I'm saying a lot. Again, I know I'm saying too much for some people. I get it. But there are some people in the room that I've said so much that they're totally lost and they never did it. And you can admit being either person. You can admit it in the private chat. But I think dy dt, like the derivative of the inner function, is omega. Just to pause for a second. All of what I'm doing right here is assuming, and this is very important. This is where people get, I'm treating t as an independent variable, and I'm treating x as a dependent variable. I'm treating t and x as the variables. But every other letter I'm seeing, a and omega, they're letters, but they're not variables, right? They're constants, meaning they might as well just be numbers. They are numbers. They're just numbers that I happen not to know. But they are numbers that are not, like what's the difference between constant and a variable? A variable varies throughout the problem. Like while this thing is going back and forth, that if you look at that graph, the value of t is changing. The value of x is changing. But the value of omega or a, they are not changing within the problem. They are effectively just numbers. So the derivative of y with respect to t is omega. It's as though I wrote y equals 5t. What would the derivative with respect to t be? It would be 5. Again, there's at least 2 people in the room that actually don't get that. and they should not be, and you, whoever you are, should not be ashamed. You should tell me privately. It's not too late for you to get it. But anyway, but if you don't tell me, I'm going to go on. So dy dt equals omega. Okay, so therefore, x equals negative a omega sine of y, which is omega t, right? Now, I took a long time to do that. I'm not going to take as long to do the rest, but that's the, well, sorry. I mean, that's the last time I'm ever going to drive all that out, I think. So you really should tell me, even text me later if you're like, all right, honestly, I didn't follow that at all. Like, that doesn't mean I'm not saying I could drop everything and teach you all of calculus oh, okay, good. Oh, well, thank you. Okay, cool. Okay, I'm psyched, Valentina. And I will go on now. I will go on and I'll be faster now. But again, last thing I want to say this, just because one person just said it made sense, and yes, that makes me happy and I believe her. I really, it doesn't mean she's speaking for everybody. You're allowed for this not to make sense. You're allowed to admit it to me later before an exam, even if there's only so much I can do about that. The one thing I won't do is shame you. It is not too late for whoever you are to admit that you never really got calculus because I'll tell you right now, if every single person in this room literally said they absolutely understood all, someone's lying. Like, then there's shame. Because whatever. Anyway, but I'm going to go on. So, okay, I'm going to go. Okay. So that's step 5, final answer. So I'm going to circle. Like, that's the final answer. That's the derivative. Oh, sorry. Oh, sorry. Oh, cool. Oh, hold on a second. So something just happened in the direct chat. That's great. Okay, I am going to go on. No, I just got something interesting in I got a couple things in the direct chat. One person had the honest, I'm not even going to read it out loud, but I was just paraphrase. At least one person basically said, like, actually, I feel like this is not their words, but someone implied, like, actually, I'm concerned about like a bunch of other things. It's clear that I did forget a lot from calculus, but this thing that you just did made sense. Let me address that first, which is great to hear. This also goes back to Panina's question before. Like, I know that a lot of us are used to, we sort of see a thing in class, we can sort of practice thing in class, but then if we really want to prepare for an exam, we kind of know in our hearts that we better practice like exercises 1 through 89 odd. Like, we're used to this idea that like, it's one thing to know the thing in class, but you better practice a million different exercises so that you could be prepared for every twist and turn that the professor's going to throw at you or whatever. Or so there might be a feeling in some of you right now, like, I get what he's doing, but if he were to suddenly give me the derivative of tangent, or if you were suddenly to ask me the product rule or something on the exam, then I'm sunk. Like, I can do this, but I'm right on the edge. I could totally respect that feeling. And yes, you don't just want to know. It's true. That's you should be cautious about that. But I'll tell you right now, all of you, to put you slightly at ease, over my experience in physics, the way we do it here, actually, what we really believe is if you really can get deeply inside the huge classic central examples of these classic central topics that we have, like, you should view what we're doing in these homeworks and what I'm doing here as the classic central examples of classic central topics. And they're classic and central for a reason, that if you really know them, then a lot of understanding does spiral out from them and a lot of applications do come. So I will tell you right now, yes, we're going to vary certain things on the exam. But if we're spending all this time on cosines and sines, I'm telling you right now, no, it's safe to expect you're not going to walk into the exam and suddenly have me ask you the derivative of a tangent. Like, I won't. Or like, if you need the product rule, then we'll need it and we'll practice it before. I mean, there will be twists in the exam, but if you can trust yourself that if you can really get inside and understand the techniques that we're doing together here, that is what I'm asking you to know. It's not just an example of a huge swath of stuff that or this differential equation that we're trying to solve here. Oh, there's going to be 2 more in class. Yes. But that would be a total of 3 in class that you need to know. I'm not asking you then to be able to solve all the differential equations in the world. That's not the point. The point is to get inside these fundamentals. So I hope that sort of so if you're getting this, don't think, well, still, that's just this. This is just 1% of the pie. No, this is the pie. Okay. Which is why the way to practice is just freaking do the practice exam like it's your Bible. That makes no sense. But don't think it's just one set of examples. Think it's the thing. Okay. Going on. So that's the derivative. That's the answer to the first one. I will speed up now. I promise. He says as he gets totally distracted. Okay. All right. So that was all A1. Now, I took a long time because it was the first one. If it was your exam, maybe you would take a long time too, because it would be your first one. You might even notice that I tended to try to use black, the color black ink whenever I was like actually solving. I tried to use red whenever I was annotating the steps, and I tried to use blue whenever I was like phrasing the question. Like, pro tip, do something like that. Something like that, right? Now I'm going to go to the next one, to question 2. I can speed up, and even if this were the exam, now you've laid out a lot of things. So now you can be faster even in the exam. Like I'm not like, all right, I'll quickly, like I'm just going to say, for step 1, DFP, C above, you can totally do that. I should have written it over here, sorry. And so I'm up to step 2. Step 2, Dif.Eq, like what's the question there? The question is, what the heck is the second derivative? Okay, now for step 3, C above, but I'll add one thing. Maybe it's I'll add one thing. We're now taking a second derivative, right? This is what I'm about to say is maybe obvious, maybe not, but if we're about to take a second derivative, like a second derivative by definition means the derivative of the first derivative, right? Like, so which means I'm writing like the second derivative means the second derivative of x with respect to t means the derivative of, wait, excuse me, let me say this again. The second derivative of x with respect to t means the derivative with respect to t of the derivative with respect to t of x. I'm going to say that one more time. The second derivative with respect to t of x means the derivative with respect to t of the derivative with respect to t of x, right? Why am I writing that down? Like, that seems utterly stupid, maybe, but there's 2 reasons I'm writing it down. One, to give me permission to just freaking take the derivative of the last thing I got and call it a day. It means I don't have to reinvent the wheel, which is probably what we would all do. But if you think about it, that's a step. The fact that we can just use our knowledge from the first thing. Okay, that's number. But number 2, look at, this is another plea here from the soapbox of math is not as arbitrary as it looks. It looks like a bunch of gobbledygook, maybe sometimes, but the notation is all chosen very carefully to actually mean something. You might, if you're like me, the first time, which I hope you're not, but the first time I ever saw a second derivative, d2x dt squared, I know that what happened in half consciously in my mind was I noticed that it was like d2x dt2, like the 2, you write in the numerator are written in 2 different places, right? You might have gotten so used to that at this point, you don't even notice it anymore. But I bet I'm not the only one in the room that the first time I saw that, I bumped. I was like, huh? Like I thought it was a typo or whatever. And then I realized, no, that's the way they write it. They put the 2 in the middle and they put the on the top and they put the 2 over there on the bottom. So what? So what? So what happened in my brain? I didn't raise my hand and ask about it. I don't think I had the guts to do that. What my brain did very quickly was my brain was like, wait, that doesn't make any sense. And then my brain was like, oh, that's another one of those stupid math things where they just like don't make sense. They just do crap just to like keep us on our toes. Okay, like, and so I memorized it. That when you write the second derivative, you put the 2 in the middle on the top and you put it in the bottom. And I memorized it. And it was another one of those millions of little things that went into my mind that just taught me the lesson. Math is just crap. Like it's just arbitrary crap. Just accept it and get it right on the test and move on, right? Which served me well until it didn't. Like until the test got hard enough that I couldn't do that anymore, right? The point that I'm here to make is no. There's actually a reason it's written that way. You can't always see the reasons for all these notations right away, but I'm here to tell you that there always is a reason. And if you assume there's a reason and you take the time to think it through, it might actually really help you trust math and trust your own ability to actually make sense out of it a lot more than just memorizing it. The reason it's written that way is that a second derivative is a derivative of a derivative. It's not multiplication. If they put the 2's in the same place in the numerator, if they put the 2 after the x and after the t, that would make it seem like the second derivative is dx over dt times dx over dt, which it totally is not. It's an operation. We are taking the derivative with respect to time of the thing that we already did, right? That's why, and so if you think about it, the abbreviation makes sense. The dt is squared in effect, but the 2 goes between the, I'm just saying this shit makes sense. And it doesn't always seem that way, but it does. And it doesn't mean it always will to you, but I'm telling you, it works a lot better if you go in with the belief that it's not just made up to annoy you or to force you to memorize it. I'm just saying. So this now means we could take the second derivative or it means we could take the derivative of the thing we got above, and we can use the same rules. So again, we'll use trig derivative and chain rule. Okay, and chain rule. Although here we want to use the other trig rule. So here, note, so I guess it still is GDP. Note that if y equals sine of x, then dy dx equals cosine of x. Now notice here, so notice in the other one, a negative sign was introduced. You could show that with pictures if you need to. But here, when you're taking the derivative of sine, you don't get negative cosine, you just get cosine. And again, most of us have memorized that at this point. You can prove it to yourself with pictures, but it is definitely true and definitely important. So this time, we're not going to introduce a new negative sign. So we're not going to negate the old negative sign. So we're going to say, to cut to the chase, so here, and this is what we did yesterday. Well, did I get the answer before? Sorry, hold on. Hello. Yeah, I did. Okay. Yeah. Okay, so we're going to get negative a omega cosine omega t, but the whole thing again is going to be multiplied by omega, right? It's still chain rule again. There's still that omega sitting there in the inner function. So to clean it up, to organize it better, and to keep all the constants, multiplication is commutative, we can bring that omega out and write this, right? So this is now our answer. Oh, sorry, and I just violated my own rule. This should all be in black. I apologize. I'm going to leave it. Should be in black, but so that's step 5. That's our answer, right, to the second derivative. Again, you can write me if that doesn't make sense, but just please, the key point here is that the omega is now squared and the negative sign did not go away, right? One derivative introduced a negative sign and the other derivative did not knock out that negative sign. That's actually quite important, but there's the answer. That's it for that. Moving on. Okay, so now that was all just arbitrary math, but now I wish I hadn't done that in the wrong color. But now we go to B. And I'm going to stop marginalizing now. I mean, that's the wrong. I'm going to stop, writing in the margin. I'm going to just, from here on in, I'm going to compress this more. This is more going to be like answers now rather than solutions. I'm going to even say that. Right. In other words, here I'm just trying to teach the math and the physics. I'm not anymore modeling for you how you would get full points on an exam. And I hope that's clear. So so if you copy from here on in anything that I do straight into your exam and then expect, don't. Okay. Oh, someone's here. Sorry, hold on. Okay. So hello. Okay. So the question is, so is x equals a cosine omega t a solution to right? That's the question, right? And the answer is freaking yes. And this is actually really the point of what we just did. What we just did was the same thing as what we did at the end of yesterday. We took two derivatives of that function, and we found that when we took two derivatives of that function, what we got back was that function times omega squared times a negative sign. How do I know, or why am I saying yes? Because, and this is what you would write.
Couldn't.
Oh, so yeah.
Wait, you were gonna write it in words?
Well, here's what I'm going to write. I mean, there's different options, but here's what I'm going to write. I'm going to say, because we just found out when we just did out the derivatives, we found out that, I mean, good question, but we got this, right? But here's my point. That is the same thing as this. And this
Is X.
is X.
Basically.
Exactly.
Okay.
Yeah, no, and I'm glad you just stopped me there. Honestly, everybody, that is the key point. Like, first of all, yeah, that's what I would ask you. Something like that is what I would ask you to write in the exam. Like, show that, like, we went through all that work to get the two derivatives, but it doesn't mean anything until you see that what we got when we, I mean, it was a really good question. What we got when we took that second derivative, we got something that looks like just a whole new function, a bunch of gobbledygook. But then we notice, oh my God, embedded in our answer is our original function x. So we literally did get, we're saying, oh yes, like the whole requirement of the original differential equation. The differential equation says we want some function x such that when you differentiate it twice with respect to time, you get back itself times omega squared times a negative. And that's literally what we got. Oh, sorry. Yeah, fair enough, Alexis. Okay, so, okay, no, totally. That's why we're doing this. So let me say, so first of all, on Christopher's question, just so you all know, it's not just because Christopher said, or wait, like, I know, I still remember to this day, wait, 1990, what was it, 99? I mean, I graduated in 19, I mean, honestly, I literally remember taking tests on this in calculus in college in like 1989 and 1990. And I remember that I got points off. I did all the stuff that they asked. I took the derivatives, and the thing that I could never see on my own because I didn't practice enough, it was this last thing that Christopher just asked about. Like, I would get to that point where d2x over dt squared equal negative a omega squared cosine omega t. And then I'd be like, okay, like I sort of see what's going on. Like, I think I did it right, but like, I don't see what this is. The key that you have to see in your mind and you have to put on paper is that, oh crap, I just got back the original x that I'm testing. I got back the original x times a constant called omega squared times a negative. That's the whole thing. So, I mean, so I'm glad Christopher asked that. But then also on what Alexa, so you want to practice that. Like that's all I can say. You want to practice that because you want to be explicit about that. And that, if I'm not careful, I can say. And like one also way to practice it, I think there's examples in this sheet, and there's definitely examples in the practice exam. One way to really see what's happening here, like part of, and this gets to Alexis's question now. Part of the problem is it feels like we're going in circles for sure, and especially when I talk so much, but it feels like you're just sort of like grinding the crank and ending up at the same place. But it would feel that way less whenever you test a solution and find out that the answer is no. It's a lot easier to see that something's actually happening here when you try a function that doesn't work when you take two derivatives and see what it looks like when it doesn't work. Because when the functions keep working like this, it just seems like nothing's happening. Like, well, duh. I mean, isn't that what and I will give you an example if there isn't one on the sheet. Like, or if you're getting bored or restless, like literally try x equals 1/2 at squared plus v naught t. You can take two derivatives of that. But when you take two derivatives of that, you get a, the letter a. There's no t's in it at all in your answer, let alone you don't get 1/2 at squared plus v naught t. Like, you can't make this substitution. When you take two derivatives of 1/2 at squared plus v naught t, you just get a constant. It doesn't mean that you get garbage, but you don't get the original function back. And that's why that thing is not an oscillator. What we're saying here is there are certain types of special functions that even when you look at their rate of change, it's themselves. Like, that's a really heady, weird point. It's so circular that it seems like it's not going anywhere until you realize not all. And it's the same point as saying, oh my God, the slope of the sine graph is cosines, and then the slope of cosine graphs is negative sines. Or same thing, the slope of cosine graphs is sines, negative sines, and then the slope of negative sines is negative cosines. Like it's the same idea. We're saying, oh my God, it changes at a rate of itself. Okay, so anyway, on Alexis's question, I'm glad she admitted that. Right, because what that word solution we're getting used to now. See, this is all reverse engineering. This is this topic of differential equations, or whatever you want to call this. We're doing stuff that you're all familiar with, but we are doing it backwards. And that is, like, you used to take questions and problems and solve them, get solutions to them. Oh, 1 second, I'm sorry. What? At 6:45, which means, is that what you, okay? So that means 1 hour and 23 minutes. I know, I believe you, I understand. And then we'll totally do Nukazan. Watch The Simpsons. Okay, well, I'm going to take a quick break soon, and I'm going to come up and help you out. Sorry. In about 10 minutes. In about 10 minutes. Okay. Approximately 8 minutes. But now I got to get back to something like that. I think we're eating into it right now. Yes. 480 seconds. Okay. I love you. Okay. Okay. Oh, but no. It's really good that Alexis asked that, because what's happening now is what we're really doing now is we're giving you answers. It's like Jeopardy. I mean, really, we're giving you answers, and we're saying, does this answer work as the answer to this original question? Or, right, I mean, we really are going backwards. When you get a differential equation now and you try to get a solution to it, you have to think backwards. And then sometimes what we're doing here is saying is this function that you used to think that you were meant to solve or something, we're saying this function is the answer to some differential equation. This function might or might not be the answer, the solution to some differential equation. Here's it's a matching thing. Here's the differential equation that we're worried about, the one that describes simple harmonic oscillation. Does this function solve that? It is a different way of thinking. It is, until you get used to it, it is confusing. Last thing to say, but I'm glad, I don't think Alexis is alone at all. I'm bumping on that, but if it makes sense now, great. When we say solution, what we mean is traditional function. When we say solution, like what we're looking for, again, when we have a differential equation, which we don't want, it's just that the physics is producing it. We don't want differential equations. Differential equations express derivatives as functions of dependent variables. That's totally not, that's not an input-output thing. We're looking for, if you give me the input, what's the output? But nature, physics laws, give us these situations where they say, well, I know you're looking for, here's the input, what's the output? What I can tell you is the rate of change of the output with respect to the input depends on the output this way. And we're like, what? Like if you look at that thing in the middle of the page, it's literally okay, I could go on, but it's not telling us what the output is. It's telling us how the output changes in response, not even to the input, but to the output itself. It is a freaking circle that we have to break. When we say solution, we mean a properly written function where the output is written as an expression that depends on the input. Solution means X as a function of T. So, but she's totally right. So hopefully that's what we're getting used to. That's what all these exercises are about, because it is a new way of thinking. And again, it's only arising, we're doing math backwards because physics laws don't give us direct functions. They give us derivative relationships. So we're unwinding them or unpacking them. Okay, but I'm glad Alexis said that. I'm glad Christopher said that. And hopefully, and also just like sidebar or last thing, and hopefully maybe in private chat, either Alexis or Christopher can tell me if they're like cool now or whatever. But just for the record too, I totally know the word solution throws us all off. But I also want you to get used to, I'm not doing that to throw you off. The more you get used to see this, you see that is the issue, that like we're not just giving weird wording. Okay, cool, fine. Okay, so I'll stop being defensive. I'll go on. Okay, cool. So that was that. So what happened now? Okay. Yeah, and we will do the break. I'm not forgetting, both for your sake and my son's sake. Well, okay. So I'm going to go a lot quicker now. Let's go to C. I think you're getting the point. Sorry. C is X equal a cosine 5t, a solution to this. Okay, so very quickly, I will do the thing, but like what, here's a sort of an example, not a perfect example, but sort of an example of here's what it's like when things don't work, so to speak. Like, so the answer here is no. The answer is no. Because to cut straight to the chase, if I take that, so how do I test? How do I know? Again, like by taking derivatives, right? I'm just going to follow the model but I'm going to do it quickly now. The model that I did up in A, if I take the function, the potential solution, the solution I'm testing, X equals a cosine 5t, right? Like given, given X equals a cosine 5t, well, then if I take one derivative, I get I get negative 5a sine 5t, right? And if I take another derivative, and if just look back in your notes from what we just did, and if I take another derivative like so the 5 now is still a constant, it's functioning just like omega. 5 is omega here, right? I mean, it's like the angular frequency now is 5 radians per second, not 5 pi, just 5 radians per second, which means, if you're really with me here, it means it's doing almost a full cycle per second, because there's a little bit more than 6 radians in a full cycle, right? Like 2 pi, like it doesn't always pi. You get what I'm saying, or you don't. But anyway, I take the second derivative and I get negative 25 a cosine 5t, right? That's the second derivative. Now, wait, sorry, did I switch from x's to t's? Sorry, is x? Oh, yeah, right. Okay. So a cosine 5t is x, right? So what I got is negative, like, in other words, like, again, like this is like the Christopher thing. I noticed that this part right here is x. That's the x that I'm testing, a cosine 5t. Okay, that's x. So when I took two derivatives, what I absolutely did get was I got back x. Oh, that's a good thing. I took two derivatives and I got back the original function. So something is going right here. Why? Because I chose cosines. So something's going on. But what did I get? I got negative 25 times x. The question was, does this solve the differential equation d2x dt squared equals negative 3x? The answer is no. What I'm saying is, in physics terms, I'm saying The differential equation seems to be some kind of harmonic oscillator. It does. And the solution that I'm trying is some kind of harmonic oscillator. Oh, yes. But apparently these are two different harmonic oscillators. More specifically, the solution I'm trying is a harmonic oscillator with an angular frequency of 5 radians per second. But they're asking me about an oscillator with an angular frequency of square root of 3 radians per second. You may or may not see what I just said. I'm going to expand on that in the next exercise. But what I'm saying is these are both harmonic oscillators, but they're not the same one. This A cosine 5t does not solve the differential equation because I was supposed to get back. So this is an example of something not working. What's my answer if I were taking an exam right now? No, the answer is after I just took my two derivatives, and what I conclude in the end of the day is 25 does not equal 3, if you see what I'm saying. So they're not, it does not solve it. Okay. Let me just look for one. Okay, and then D, I'm gonna go fast now too. D is just really asking me to expand and justify what I just said. I mean, D, I just did. D, see above. Okay, it's just breaking it down, the process. I think, hold on, I'm not forgetting it. Okay, all right, I'm going to quickly do E. Then we are going to take a break like promised, 6:45. I'm going to do E quick. I don't think it's a huge deal. Then we will take a break. And then I may or may, and then we're either going to do homework 3 or I might do F first. I have to think about that. But all right, so E, let's do E quickly. E is more, and I don't know why the numbering got messed up. I apologize. It says E 3, 4. It should just say 1, 2. That's a mistake. But so E says given X equals A. Let's see. Now it's just starting again. Any time up until now that I've said the letter A in this math stuff, I could have said the letter X naught. I hope I made that clear yesterday. I mean, they're interchangeable. They're both constants. They both mean the initial / maximum value of the dependent variable. Now, up until now, we've been talking about this omega thing, just a constant, right? It's just the rate of oscillation. But okay, so now it's instead it's using K and M like in the homework 1B. Okay, they're still just constants. Whether you call it omega or K or M or K over M, like a constant divided by a constant is a constant. So if I take one derivative, if I take one derivative, same rules as before. Again, this is not a full solution. I'm just banging out answers here now at this point. If I take one derivative, oh, wait, something's in the chat. Did I miss? Wait a minute. Oh, sorry. Wait, how long ago was that? That was a million years ago. Yes, sorry. Hello, maybe I can't. Wait, hello. Okay. Is this? Sorry. Thank you for asking, Valentina. Sorry. Tell me when. Okay, great, awesome. And that's huge points, a Googleplex points. Awesome. Okay. All right, so if I take one derivative now, same deal as before, I'm going to get negative A square root of K over M times sine of all the nonsense in between, I mean, all the mishigas, all the stuff. That's the, and if I take the second derivative, I do it again. So the square root of K over M comes out again, and I get this. And those are answers, I think. And this is all getting hopefully somewhat repetitive to you. I mean, hopefully you're feeling that this is somewhat repetitive. I mean, it is. But why? Why did I just do that? Well, it didn't actually, so what it could have then asked, the reason I just went through that is, if you notice, let's go to the next page. So all right, so D2, so I'm now saying something that it doesn't say in the sheet, but note, D2x dt squared equals then negative k over m times a cosine square root of k over m times t, right? I just did multiplication as commutative. I just rearranged where the a and the k over m were. So again, just like before, the same pattern that we're seeing over and over again, this whole thing here is x. So even though the question didn't ask, just note that x equals a cosine of square root of k over m times t is a solution to d2x dt squared equals negative k over mx. What am I trying to say? I'm trying, which was our original whole physics question that prompted all of this math. I'm saying, now let me be clear about that. I mean, I know some of you totally already get this. Some of you don't, it's fine, but it is really important. I'm saying whether you call it, here's what I'm saying. I mean, this was our original physics question, the thing that's written at the bottom here. This was this is Hooke's law for us, for specifically a spring, right? The second derivative of x equals negative k over m times x, where k is the spring stiffness and m is the mass on the spring. K over m is a constant. The solution to this is x equals a cosine of square root of k over m times t. Just like, so this is just like saying that if you have this, the solution is this, right? What I'm trying to say, I'm trying to say two things. Number one, I'm saying what I said yesterday, which is omega over here is this name for a rate, an angular frequency, a rate at which something goes back and forth and back and forth. But it's a constant rate. It's a number. It's measured in radians per second. Over here, we have these constant parameters, these constant descriptions of a physical system, stiffness and mass. Number one, what we seem to be finding here is first of all, okay, we are gonna take a break in a couple minutes. I'm not forgetting, and it would be when I'm done with this problem, but there's two huge takeaways from. The first takeaway is the rate of, remember, omega is angular frequency. It's radians per second. It seems a little obscure when you first see it, but remember, angular frequency is just 2 pi times regular everyday standard frequency measured in hertz. And standard frequency is the reciprocal of period, right? So omega is a rate of oscillation. It's just measured in funny units. but omega is a rate of oscillation. The first takeaway that we're getting from here, if we see that the math of omega is the same as the math of square root of k over m, like the differential equations work the same. It's the same solution as long as one is equal to the other. What we're saying here is the rate that this mass goes back and forth on the spring is fully determined by the mass amount, the heaviness of the mass, and the stiffness of the spring. Like we're saying, radians per second is fully determined by newtons per meter divided by kilograms. That's true. That's completely true. It's not obvious. It's part of the thing that we're discovering here. To be more specific, first thing I'm saying, and I will wrap up soon, I'm saying that the parameters of the system, the material properties, the material measurable properties of the system, i.e. the stiffness and the mass, things that you could measure, the measurements that you can make of the ingredients that you put together to make this experiment, to make this system, those unchanging measurable properties of the system fully determined the rate at which the system oscillated. I think that's interesting, but the only reason I think that's interesting is as opposed to what? Like you might be saying, oh, okay, yeah, the rate of oscillation is fully determined by parameters. Like what else would it be determined by? Like why is that a big deal? Well, as opposed to this. Parameters are not the only constants involved in this system. K is a constant parameter. It's an ingredient, stiffness of the spring. Once you put the spring down, you measure the stiffness, no matter what the thing is doing, the stiffness doesn't change. Once you put the mass down on a scale, and you set the thing up, the mass of the mass doesn't change. But those aren't the only constants of the system. There's this other constant called amplitude, A, or X naught. That's a constant as well, right? But that's not a parameter. That's a constant, like amplitude, okay? Amplitude is what's known as a constant of configuration. It is a constant. It doesn't change throughout the oscillation of the system. But what it is how you set up the system, how you configure it. It's not an ingredient of the system. It's how you set up the system. What I'm saying is, oh, and I see there's something in the chat, and I'm not forgetting about the break. I'm going to wrap this up and maybe the other sub point and then the chat, and then we'll break. But hugely important point here, and about to be a definition and an equation, is I'm saying this, any oscillation that is governed by the differential equation that we are here talking about, the second time derivative of the variable, of the dependent variable, is directly proportional to the variable itself, that equation that we're dealing with here, whenever that is true, that sets up a kind of oscillation where it doesn't matter how far back you bring the mass initially, it will still take the same amount of time to go back and forth and back and forth and back and forth. Note it, what I'm saying is omega, comma, f, comma, t, the rate of oscillation of this thing, omega specifically, like remember, omega, like f is based on omega and t is based on f. They're all like, well, what is omega? It's the square root of k over m. What does omega not have in it? It doesn't have any x naught or any a in it. I'm saying omega is not a function of a, or omega is not a function of x naught. The frequency is independent of amplitude. It doesn't matter how far back you hold this mass. You could hold it at 15 centimeters and it'll go, or you could hold it at 45 centimeters and it'll go, either way, it's going to be tick tock, or tick tock, tick tock. Doesn't matter how far it's going. Doesn't matter how far it's going. It's going to take the same amount of time to go. That's a revelation. That's why we build clocks out of this thing, these things. Oscillators keep time irrespective of space. They will take the same amount of time to go back and forth, regardless of how far you're asking them to go back and forth. This is actually a very big point. Frequency independent of amplitude is the defining feature. It's what we mean by what we're going to call from here on in simple harmonic oscillation. Like anything that goes back and forth is called an oscillator. But this type of oscillation that goes back and forth with a period that is so constant, a frequency, an angular frequency that is so constant. How constant is it? So constant that you can't even tweak it or change it or affect it by changing the amplitude. You could say to the spring, okay, that's very good that you're going back and forth this fast when it's 15 centimeters, but now I'm going to mess with you. I'm going to pull you out to 30 centimeters. Now I'll see you fast. You go, the spring says, well, even though you're pulling me farther, and even though you're asking me to go farther, guess what? You're giving me more potential energy. So on average, I'm going to have more kinetic energy. So I'm going to freaking go faster for those bigger swings, and it's going to work out. I'm going to go just faster enough that it's going to work out to the same amount of time. If I am a simple harmonic oscillator, what I am is a clock. I'm literally the essence of timekeeping. I keep time regardless of space. That's why you will build clocks out of me, the spring, or me, the pendulum, or me, the RC circuit, electronic clock, digital clock, right? Because if I'm an oscillator, I keep time regardless of space. If I'm a harmonic oscillator, I have a frequency that is independent, that is fully determined by parameters, like omega equals k, square root of k over m. There's no x naught, there's no a in that formula at all. That's my big point. Wait, I know we have to take a break. I also know I have to see in the chat. But there's one, I'm going to say one last thing just to wrap this whole point, because that was like sub point one. Right, I think I put a sub point one on it somewhere. Yeah, one. So, and I know there's something in the chat. It's probably like, could you please go back, or could you please like stop yelling or something? But sub point two. This is true in general. Everything above is true in general. If the letter Z stands for any arbitrary general, I basically said this at the beginning of class, but general dependent variable, then if d2z dt squared equals negative some constant times z, right? If the second time derivative of any variable, any measurable quantity, z, if the second time derivative equals the negative of z times some constant, then z will oscillate harmonically at a rate. It'll oscillate cosinusoidally at at a rate of the square root of that constant I should probably write the figure on the next page, but I'm saying whatever that I'm saying if d2z over dt squared equals negative any constant times z, then z will oscillate, like the value of z will oscillate harmonically at a rate of omega equals the square root of whatever that constant is. Whatever the constant in the differential equation is, the square root of that is the rate of oscillation, the angular frequency of oscillation. That's why, and this is, I swear I'm closing with this, I mean, closing until the break and getting the chat. That's why we often write the differential equation as d2z dt squared equals negative omega squared z. We write the constant as omega squared because we're just anticipating. We could have called it anything, the constant, but we know that whatever that constant is, like if the constant is k over m, then the angular frequency is square root of k over m. If the constant is beta, then the angular frequency is square root of beta. So whatever that constant is, we tend to just write it as omega squared because we already know now that we've solved it once that the rate of oscillation will be the square root, the omega will be the square root of whatever that constant is. So we write the constant as omega squared. That's the point of all. All right, I'm gonna look in the chat. We're gonna have a quick break. Oh, sorry. Oh, okay. But she never mind. She sees it will come. Okay, sorry. Okay. Hopefully this is somewhat clear. That's the point of that problem. It's 5:52. I know 8 minutes is weird, but let's take a break for 8 minutes. I'm gonna start again at 6. I mean, if you come back at 10, I know it's technically, but whatever. At 6, I'm gonna start talking again. Okay. Okay, let's see. Okay, I'm back. I don't know how many of you are back. Let's see. Okay, you all are being very patient. You're all being very smart. You might ask yourself, do I always say that? No, I don't. I definitely don't always feel it. Okay, but I am maybe just and we're gonna all right, so first of all, could you just raise your electronic hands if you're back and with me here? I know it's not exactly a time. Oh, great. Thank you. Thank you, Michaela. Thank you, Samantha. Thank you, Christina. Thank you, Allison. Thank you, Dante. Thank you, Valentina. Thank you, Juliana. Thank you, Bradley. Thank you, James. Thank you, Bree. Thank you. Okay, awesome. Who else did I not say? Okay, thank you. Okay, so you're here. Also, now and again, you can put things in the private chat if this is or is not working for you, whatever. I'm going to shift gears now. I'm going to go to homework 3 now. Now, by the way, I know homework 3 is not due to tomorrow. Some of you are still working on homework 2. I totally get that, but that's fine. And you can still, as many of you, so this will help you get a jump start on homework 3. Hopefully, what I'm about to do, hopefully, it's helpful. Of course, you could still hand it in with help from the class. But I'm not going to do all of homework 3. I'm just going to shift gears now and show you how this is all related. And I am going to tell you again, you're going to notice if you open up that practice exam, I'm just going to relabel it practice exam. I mean, that exam, if you didn't hear me before, actually, let me just ask this now. The exam that is already in your Google Classroom, the exam that says midterm from spring of 2023, I'm going to relabel it any minute now as practice exam. Like that is your practice exam. I might make some modifications, but that's basically what you're going to do in lab tomorrow. So if you want to get a jump start on it tonight, Quark plus America. Just raise your hand if you heard me say that is your practice exam for tomorrow, basically. Awesome. Thank you again. Same people. Thank you. Awesome. Thank you. Okay. So you'll notice when you open that thing, one of the problems in there is homework 3. I mean, well, you'll know that you know what's going on if you see what I mean. Like one of the problems in there, I think it has to do with a capacitor or something like it's not about a weather system. It's about some completely different object, like a capacitor. And by the time you take your real exam, depending on how lazy or not lazy I am, I may change the wording again, and instead of a weather system or a capacitor, maybe I'll make up some other thing like I don't know what, a pressure differential in a weightlifting device or so. Pardon me for a second. Hold on. Sorry. Okay. So right now, or at some stage, if you look at homework 3, which you're working on tonight, and you look at problem, I'll tell you right now, problem 1. Is it 1? Thank you. Okay. If you look at problem 1 in the exam, depending on where you are, you might think that they're very different problems. One's about a capacitor and one's about a weather system. But the more you see what I'm trying to say in class, the more you see the math of this, you'll see they're the same problem. And that's part of what I'm trying to get you to see. We are learning the math of simple harmonic oscillation. We're learning that in a physics class because it turns out that throughout the physical world, there are countless examples of systems that are fundamentally boiled down to simple harmonic oscillators, which really means in English, there's countless systems in the physical world that at their core are behaving just like an ideal spring with a mass on the end of it. Like the whole course starts with a physical spring with a mass on the end of it because we're then trying to say there's lots of things that behave according to the same physical principles as that, which in turn mean there's a lot of systems that are behaving according to the same mathematical underlying laws as that. And for what it's worth, a PChem, which many of you take next, PChem is really like a secret code for mini baby quantum physics. Not baby, it's not baby at all, actually, but like it's mini quantum physics. And quantum physics is all ultimately about atomic and subatomic oscillators that are obeying a differential equation, much like this one, ultimately a slightly more complicated differential equation known as the Schrodinger equation. But this is at the core. This harmonic oscillation is at the core of all these things. And once you see the math of that differential equation and you recognize what the solution looks like, they all work the same. So that said, if I turn now, if we together turn our attention to homework 3, I'm like flipping around. Homework 3, where'd it go? Sorry, homework. Yeah, homework 3. Okay, and again, I'm now in the interest of time, I'm going to trust that you're getting the 5-step method. I'm not going to drag it all out for this right now. I'm going to give you an answer, not a solution. I'm not, well, I'll give a quick diagram. I mean, so homework 3, we have a weather system where the temperature is designated capital D, as in degrees, and the degrees are fluctuating back and forth in time according to the differential equation, right? So here, in other words, here, T is still the independent variable, but now they're using capital D, slightly unusual, but they're using capital D as is the dependent variable. And capital D stands for temperature measured in degrees, right? And apparently the temperature obeys this differential equation. If you're following everything I just did with the last few exercises of homework 2, and if you're following all of like the work we did yesterday for the last exercise on homework 1, what we're ultimately trying to say is anytime some dependent variable can be described by this equation, then that dependent variable is oscillating harmonically in time. Like you would write, I'm going to say this, in your exam, you would write the givens for step 1, and you would provide a diagram that I think, if you're following me, you would realize your diagram would look something like this. And the initial or maximum value, the y-intercept, is given in the problem as 200. The D0 equals 200 degrees Celsius, right? And for one of your GDPs, you would say something like, okay, so I'm going to skip to GDP. You would.
Wait, sorry. Can you go back to the previous?
Oh, sorry. Oh wait, does it make?
All right, that's good.
Oh yeah, okay. So, and I'm going a little bit all over the place here. I'm not being clinical about my step 1, step 2 exactly right now. But what I'm saying is it was given in the problem that the initial value was 200 degrees Celsius. It was given in the problem that the Celsius degrees, the temperature, obeys this differential equation. Like those were the givens. Maybe it's not immediately obvious that the graph is a cosine, except that I'm going to say now, based on everything we just derived in homework 2, I'm going to say, like in general, like if you, someone's here. Sorry. In general, if you have this, then, right, this is the mathematical like language for what I just said in English before, that in general, if you have some variable z that obeys that differential equation, or that can be described by that differential equation, which is to say that its second time derivative equals negative times a constant times z itself, right? Like omega squared, part of what I'm trying to say over and over again, that does take some getting used to. All of this, once it clicks, but until it clicks, it doesn't. Okay, and again, I want to say over and over, I understand that for different people in the room, it's going to click at different times. If it hasn't clicked for you yet, stay with me. And please understand, eventually this clicked with me, but it didn't click the first 40 times I saw it. So I'm going to do it. What I'm trying to say, part of what doesn't click with people for a long time is omega squared. Every time I write that differential equation, when I'm writing it in general, omega squared is just a number. Don't be thrown off by the fact that it's written with a square. Don't think that this is like a quadratic equation or something like that. We're not squaring the variable. Z is not squared. We're saying that the second time derivative, in fact, is directly proportional to the variable. Like Z is the variable. Z means any variable at all. It's not being squared or cubed or anything like that. Omega is just some number. And then we're squaring it. So that's still just some number. Omega squared is just an abbreviation for some constant number. Okay. But the reason, so we might as well have just written it as C. That might have made a lot of us a lot happier if we just wrote it as C. And in your notes, you can for a while you're getting used to this. But the thing that we're saying that we just figured out, like yesterday and earlier today, the thing that we figured out is whenever this differential equation applies to a situation, to whatever variable is being measured in time, whenever that differential equation describes how the variable is acting in time, then that means that the variable, the measurement, is varying cosinusoidally. It means that the value of that variable is oscillating back and forth at a rate that is constant, and that is so constant, it doesn't even depend on how big the oscillations are. That rate we call omega, and what we're saying mathematically is that rate will always be, it turns out, like this is what I mean when I say that in general, Z equals Z naught cosine omega t. What I'm saying is that Z, whatever Z is, will go back and forth cosinusoidally at a rate of omega, like omega t, right? Radians per second times seconds equals radians. It'll go back and forth at a rate that is the square root of that constant. So it's like playing Monday morning quarterback. We're retro engineering, we're reverse engineering. We're calling that constant omega squared because we already know in advance that the square root of it will be omega, right? But again, all of this is like very backwards thinking until you get used to it. And if you want to get used to it, it helps to recognize that it is backwards thinking. If you want to get unconfused, the first good thing that a lot of you have already done in chat with me is you've already admit at any moment when you were confused, or you've said like, oh, that word solution threw me off. It's really good. This is not obvious. I'm trying to break it down, but it is weird way of thinking. That's why there's entire courses devoted to it called it, right? So what I'm saying is that omega, so I'm saying, to apply to this problem, in general, our GDP is whenever some variable Z obeys that differential equation, then a solution that works is Z equals Z naught cosine of omega t, where the omega, the angular frequency, the radians per second that I'm thinking of is literally the square root of whatever that constant is. What does that have to do with this problem? It has to do with, so first of all, it's why my diagram is a cosine function, because I was told in this problem, I was told this new thing about weather. And when you first look at this homework, you really, I'm not being sarcastic when I say, if you first look at the homework for the first time or 2 days ago, or whatever, and you're like, weather? When the heck did we learn about weather? Like, what is he talking about? Weather system? What chapter is this in? Right? I mean, you might, I don't know, you might have read it. Or then you get to the exam and it's all of a sudden talking about capacitors. And you're like, wait, when did we learn about capacitors? What the heck is it? But the point is that what we're saying is we got some system that we've never seen before, but apparently it obeys this differential equation. And the power of math and physics is that we can do things that we've never done before if we've got an underlying way to describe them. So this differential equation literally right away tells me, according to GDP, so in other words, here, so now I'm doing step 4, honestly, in a way, step 4 here, this is step 4. Here, and I should be in black, sorry. Here we have d to d squared equals negative 121d. So what you might write in your exam or whatever is you might say, so here, in other words, here, like d is z, so to speak, if you like, and 121, if you like, is omega squared, right? That's what I'm saying. I hope you see that. So I'm saying,
I'm sorry. Sorry to cut you off.
No,
That makes a
please
whole
do.
bunch of sense. That makes a whole bunch of sense.
Okay.
And I'm just curious though, what is Z naught in this case? 0? Or
Oh,
it can
sorry.
be 0?
Okay. In this case, Z naught, or in other words, really, D naught will be 200. Like great question. In this case, so I'll write that in a moment. But yeah, in this case, like if Z is D, if Z means the general dependent variable, the variable that D, so in this case, that's D, and they tell you in the problem, only because they tell, like I wouldn't know, except
Oh, okay, I see now. I see the problem. All right, say less. I see the problem.
oh yeah, so you're good. Oh, okay, so we're good.
Okay, I'm good. Yeah, thank
Cool.
you.
No, thank you. And by the way, to everybody, I just also want to know, and I also see there's a question in the chat, but please, everybody, like, so he asked a question now, and he even very politely, like said, I'm sorry for interrupting or cutting him, but please, for everybody, I love it. Like, it's nice and it's respectful to apologize for whatever, but like the more it's better. I will go on forever if people don't cut me off. I forget. I mean, it's good. Please follow his lead. Like, it's not rude. Even if even if I spaz out for a minute, I'm going to spaz out no matter what. I'm a spazzy guy. Like, really, any kind of interruption is good for. I mean, if it's on the topic, which obviously that was. Okay. So speaking of which, there's something else in it. It's not rude, is what I'm saying. How do we know it's something in direct chat? So there's a question in the chat, in a private chat, in the direct chat, that I think I understand. How do we know the way which this system behaves based on deriving a differential equation? I think I understand what that question's asking, or I'm going to interpret it. Here's what I'm saying. The question gave us a differential equation. And what I'm trying to say is, part of what I'm trying to teach everybody, what I want us all to learn is, that differential equation has a form that we've now learned in this class. Like, what they said, d2d over t squared equals negative 121d. I'm saying that what we're learning in this class is this equation right up here. Partly what I'm trying to get across is I want you to see that those are one and the same differential equations. Anything we've said about the differential equation that we're solving so far in this class, the differential equation for harmonic oscillation, I want you to be able to recognize it, whether it's written with X's or Z's or D's, whether the constant is written as omega squared or K over M, or a number like 121. Now that's easier said than done. I want you to see that the equation that is written in this homework, in homework 3, is the equation we're learning in class. It's just that we're treating D like it's Z, and we're treating 121 like it's omega squared. And it's very fair. Like, so how can you recognize that? Like, how do you know that D is Z? And what the really important thing is, to everybody, I'm saying, to the person who's asking this question, but to everybody, the thing you have to get used to, the reason I can say it doesn't matter whether it's Z or X or D, the thing to get used to is, what matters is that it's the dependent variable. The real secret thing, honestly, is that you really have to understand how functions work. You have to understand whether we're using letters or numbers. The big lesson here is how to distinguish a dependent variable from an independent variable, then how to distinguish variables from constants, and then constants come in at least three types. They could be a number, they could be a letter that stands for a number, that letter could be a parameter or a configuration constant, right? That's what I'm trying to lay out. Is it's not really the symbol we use. It's not really whether it's X or Y or Z or D. It's whether it's a dependent variable or not. And that's what it takes time to get used to. But I will say this, that maybe that's a lot what I just said. To the person who just asked this in direct chat, and to other people who have asked very fair questions also in direct chat, here's the thing. Yes, I want you to recognize our differential equation, even when it's in a disguised form. That is part of your goal, is to recognize our differential equation for harmonic oscillation, even when it looks disguised. That's the bad news. You got to recognize it, even when it's disguised, even when the Z's are written as D's or the X's are written as Z's or whatever. That's the bad news. The good news is I'm going to tell you right now, at least for this exam that you're taking, there's no tricks up my sleeve. You're not going to get other differential equations. I promise. It would be reasonable for you to worry about that. I'm telling you right now, this is all about unpacking the differential equation for harmonic oscillation. We're going to get more a little bit later. But for this exam, at least for the first 3 problems of the exam, we're studying this one. So that's a big hit in the exam. It's not choosing one versus another. There's not going to be a new, you get my point. Okay, so you're just looking how to relate back whatever I give you to the differential equation that we are learning, which is the one for harmonic oscillation. The thing that we're saying is, if this differential equation describes a system, then the variable, the dependent variable, oscillates harmonically at a rate of angular frequency that is the square root of whatever is the constant in the differential equation. And you might say, what if there is no constant in the differential equation? Then it's not that differential equation. What makes this a differential equation is that the second derivative equals negative times a constant times the original variable. What this secretly is just Hooke's law written mathematically. This is all a big exploration of what happens when you accelerate at a rate that is directly proportional to where you are. This is all about A over M equals negative KX. MA equals negative KX. Your rate of acceleration is directly proportional to where you are. That's what it means to be a harmonic oscillator. So anyway, okay, so for this one, and I'm looking at the time, I promise. For this one, for at least for homework 3, what you write down, if it were in the exam, is you give me like a cosine graph and you start explaining in your best language. Now, see, again, here I'm starting to go off page. I'm just talking now. So the more that you understand my talking, the more you can put it into your words or your equations on the page, the more you can show me I get how harmonic oscillate, how this differential equation works in general. I get that the solution. So here on the next page. So here, what we're saying is if d2d dt squared equals negative, 121d, then here, what we're really saying, and this now goes back to Christopher's question and somebody else in chat, what we're really saying is that d equals d naught cosine omega t. What's omega? Well, d naught,
so basically.
Oh, sorry, go. Yeah, go.
So it's basically 200 cosine and square root of 121, which is 11.
Exactly. Yes, that is the whole point. That is the whole point. Yes, 100%. I'll write it one more time. Like the key to solving any of the questions that now come for the rest of this problem is realizing that if I gave you d2d, if the physics data said that weather acts like this, by the way, it's not crazily unrealistic. I mean, some of these numbers are a little crazy, but the whole situation is not crazy. If the weather data, like autograph said, d2 squared equals negative 121d, the big breakthrough insight is just to go, oh, then I guess d oscillates cosinusoidally at a rate of 200. I mean, and yes, like Christopher asked before, the 200 it was just an initial value given in the problem. There's no way I could have divined that, but it was given in the problem that d naught is 200. So d equals 200 cosine of 11 times t. Where did 11 come from? It's the square root of 121. The square root of that constant is the omega. And once you get that, it is that easy. Honestly, we've been spending 3 days building all this up, doing all this work, so that now we have this really, once you get it, it's this tool that's really easy to use from now on in life. Like once you see that differential equation, then you got a cosinusoidal oscillator whose omega is the square root of whatever freaking number was, whatever constant was in the differential equation. So yeah, that's where he got the 11. It's the square root of 121. Now you have to explain that on the exam, at least the first time you do this. You have to show me you get why. But like once you get it, you're almost going to be, you're not even going to know what to explain because you're going to think it's so straightforward. It's just that we now know how to solve this differential equation, and the solution works the same way every time. So there we go, right? Now, I'm not going to solve the whole rest of the problem. We've got like 20 minutes more. I want to, but I will say, like, what I'm really saying now is, omega equals literally 11 radians per second. Therefore, I'm going to tell you, right, I'm still in GDP land here, if you like, or well, sort of. I'm going to say right away, if omega equals 11 radians per second, well, first I'll say it's in English, then I'll write it down. What does that mean? It means the thing is cycling at a rate of 11 radians per second. What is a radian? Remember, a radian is basically a sixth of a cycle. Like, what? Where'd I get that? Remember, 2 pi radians is a cycle. 2 pi is a number. It's a funny number, but it's a number. 2 pi radians is like 6.28. So part of what I'm trying to say is you don't have to express radians with pi's. It's just that the number of radians that make up a circle is exactly 2 pi. But there's still a such thing as 1 radian or 2 radians or 3. So this thing is cycling at 11 radians. That's 11 radians per second. If there's a little bit more than 6 radians, in a cycle, I could just eyeball this, and it's my mind. What I'm saying is, oh, this thing is cycling at a rate of a little bit less than 2 hertz, right? I'm going to write that down in a minute. But if you want to picture, this thing is doing a little bit less than 2. I mean, yes, this temperature is cycling at a rate of a little bit less than 2 hertz. What does hertz have to do with temperature? I'm saying it will, like, every second, it'll do almost 2 full cycles from its original temperature all the way to its opposite temperature, all the way back to its original temperature. It'll go through almost 2 humps on that cosine graph every second, because it's a little bit less than 12, because a full cycle would be like 6.28 radians. Well, let me write this down. So I'm saying F equals F by definition, standard frequency, F by definition equals omega over 2 pi, right? Equals 11 radians per second. I'm just writing this down. You'll see what question I'm answering in a second, but I'm just writing this down to try to make this clear. 11 radians per second over 2 pi radians per cycle, right? There's 2 pi. The key conversion factor to all of this, the way to make sense out of all of this, is just always remember there's 2 pi radians in every cycle. And 2 pi is a number. It's like 6.28. So that means what 1 radian is a little bit less than 1/6 of a cycle. That's all it is. I can't emphasize that enough. A radian is just a little bit less than 1/6 of a cycle. That's all of what it means. So if I do this, then the frequency, the standard frequency of this thing, measure this, the radians cancel out. And what I get is something like F, I get that the standard frequency F is approximately 1.75 cycles per second, right? I mean, because you have per seconds over per cycle, so that, when you divide by a fraction, you multiply by its reciprocal. So the cycles flip up and the seconds flip up, and you get 1.75 cycles. In other words, the frequency is approximately 1.75 hertz, right? That's what that means. So like we said before, a little bit less than 2 cycles per second. That's what 11 radians per second means. And then to put it even in more perspective, then T period by definition is 1 over the frequency, right? So it is 1 over 1.75 cycles per second, which approximately equals, I should remember at this point, but I don't. Oh yeah, like all right, like, yeah, 5. So T, just gonna write it up here. So T equals approximately 5.71 seconds per cycle, but seconds. Now, Why do I just do, first of all, I did all that just to give you perspective on what this all means. But second of all, I believe that answers this first question. The first question on the sheet is in seconds.
Isn't it 0.
Isn't it 0.571?
Wait, maybe so. I might have missed it. But it's 1/2. Yeah, you're probably right. Wait, what? Oh yeah, you're right. Yeah. Sorry, I skipped a decimal. Yes, it totally is. I'm sorry. Yeah, I knew something was weird there. So you're absolutely right. Thank you. Another good reason to interrupt to. Yes, he's right. I was off by a decimal point. Sorry, that makes a lot more sense. Wait, did it again. Yes, 0.571, which yes, because 1/2 is close to 0.5. Yes. Thank you. And sorry. Oh, and Valentina, thank you also. So yes, the very first question on the sheet is in seconds, find how much time will elapse before the very next time the temperature returns to 200C. That's just a lot of English to me. How much time will elapse before a full cycle of temperatures elapses, before it goes back to its original temperature. And that's it. That's the period. How did I get the period? I flipped. Sorry, go. I'm sorry, go.
Couldn't we seeing that we know the angular frequency, couldn't we just say, because we know angular frequency is equal to 2 pi over the period, couldn't we just say the period is equal to 2 pi over angular frequency?
100%. No, totally right. And you can on the exam. Yes. Just to be clear to everybody, Christopher's saying, wait, didn't I sort of do an extra step here? Like, did I really have to navigate through standard frequency in order to get this answer? No, I did not. He's right. And even on the exam, you could skip straight to that step and just go that omega by definition has to be that omega has to be 2 pi over t. Therefore, t has to be 2 pi over omega. You can absolutely do that. The reason I drag this all out is just to try to be teaching this to everybody, to show how it's all connected and so that we could picture it. But yes, no, he's absolutely right. I did more steps here than you actually have to. Yes. So what else? But to everybody now, and we have 13 minutes, I'm going to back up to something else now, but I think we're covering a lot of ground here. Again, if it's starting to seem repetitive to you, if it was originally like nonsense, and then it started becoming clear, and now you're like, now it's so clear that it's like annoying, like he's doing the same thing over and over again. Good. First of all, good. I mean, not good that you're annoyed, but good, then you're seeing the point. Once it clicks in, you see that it's all the same. That's always the lesson in physics. We're trying to show that a bunch of things that look different really aren't. So you're in the right place if it's starting to look repetitive to you. If it's not yet, that's fine too. It will. But the other thing is, notice that the whole thing hinged really, like everything and the whole rest of this problem. I'm not going to do all the rest of it right now, but all of it pretty much hinged on knowing that omega was the square root of 121. That's like the whole, and that's really what we're saying is once you get that and that's why I keep writing at the beginning in the notes, like if you recognize that differential equation, if you're not thrown off by whether it's an X or a Z or a D, if you just get that the differential equation we're talking about is that the second time derivative of some measurable is directly proportional to that measurable. If the second time derivative equals negative times a constant times the original thing, then we're talking about harmonic oscillation. And the rate of the oscillation, measured in radians per second, will be the square root of whatever that proportionality constant was. That's our whole lesson here. It took us that long to get there, but that's what the lesson is. And again, once you get it, then you'll feel like, I don't even know what I get. It just seems so straightforward, but that's where you want to remember all the steps and break them down at least one time to explain to me in the exam. Now, we've got 11 minutes. This is maybe going to be a little bit jostling, but with the 11 minutes, I want to go back and do one more exercise from homework 2. Again, this is all technically, homework 3 is technically due tomorrow. I want to go back to homework 2. And again, I also want to remind you, since we're going to run out of time in 11 minutes, no, I'm going to do it right now. In Google Classroom, I'm going to right now relabel that exam that is there. I'm telling you right now is your practice exam. I mean, I might still make some slight changes to it, and I will make changes when it becomes your real exam, but that is your practice exam. And if somehow I like fall asleep and don't communicate with Professor Talley, I mean, I will, but that is the thing. Hold on, I'm just going to change the name right now so there's no confusion. The practice midterm exam. Okay. So if we get cut off, that's what you're doing tomorrow in lab. And again, it doesn't count for a grade. It counts for practice, like it's for practice, but you should go to town with it. Okay, so what I want to go back to now is homework 2 really quickly. I want to do one on purpose. I want to go to one more exercise on homework 2, the very next exercise. I'm going to do it somewhat quickly. It's not hard, but I want to make a point about it. So now, bear with me for 10 minutes. We're going to go back to homework 2. Hello. Exercise F of 1 of derivatives, where it says, given x equals a cosine omega t plus 3.5, it asks you to find the 2 derivatives. Okay, and then it asks you if that's a solution. Okay. So my color scheme has changed here now. Black means the problem. Now I'm going to do it in blue. So it's asking me to take derivatives. I don't know why, just whatever. It's asking you to take derivatives. Okay. That 3.5. That 3.5 is just a number. It's an arbitrary number. It could have been any number, but it's a constant number. And I'm going to tell you right now, to cut to the chase, if you're following everything I'm saying, that number better be measured in radians for any of this to make sense. It has to be measured in radians because omega t is measured in radians, and you can only add radians to radians. You can't add kilograms to radians or whatever. So radians plus radians equal radians, and then you take the cosine of the whole thing, all of which must be in radians. So that 3.5 is some number of radians. It could be any number. The question is, what impact is it going to have on all these derivatives? Okay, so I'm going to do, so again, I'm just writing it, x equals a cosine omega t plus 3.5. So I'm going to take the first derivative. I'm going to use all the same rules as before, trig derivatives and chain rule and all that. So I'm going to get negative a sine of whatever's on the inside. But then by chain rule, right, I'm supposed to multiply my whole answer by the derivative of whatever's on the inside. Now I'm going to say this quickly. You might have to think about this or ask me again tomorrow at the beginning of class. But the derivative, if 3.5 is a constant, if it is a constant number, then it's then it's the same thing as though we had said omega t plus 0, right? The derivative of the inside is just omega. In other words, if you have the function y, I'll just write this here. If you have y equals mx plus b, then dy dx is m, right, plus 0. The derivative of a constant is 0. There's a million different ways I can explain that. For the moment, I'm just going to say and ask you to think about that extra constant term in there did not change the derivative of the inside at all. The slope of that inner line is still just omega. So, therefore, the derivative of the whole thing, once I'm including chain rule, the derivative of the whole thing is negative a omega sine omega t but plus 3.5. Like the 3.5 still gets carried along for the ride of the inner function, but just not for the derivative. Okay, again, if I'm going fast right now, just make a mark of this and ask me tomorrow morning or think about it. But now I'm going to take the second. Oops, someone's here again. Wait, so, okay. Oh, no problem. Oh, cool. Wait, there's people. Oh, I missed. Oh, sorry. Oh, sorry. Oh, I totally missed all this chat, but it looks like you all helped each other. Whoa. Okay, Allison's cat. That's hilarious. How did I miss all this? All right. Sorry. Hello, Allison's cat. Let me introduce you to my cat, Meowscarada. It's a magic Spanish cat who evolved from Florigato. Okay. So the second derivative of this now. The second derivative, just do that again. The second derivative of that is do the same thing again. I'm going to do it sort of quickly. The omega comes out again, so you get omega squared. right? The sine turns to a cosine, so we get cosine of omega t plus 3.5. In other words, in both those times that I took the derivative, the 3.5 did not affect taking the derivative, but it did sit there and get carried along for the ride. So I can say now, so those are my answers, first of all. I mean, those are the answers to the two derivatives that's being asked. Sorry. Right, okay, again, I'm going a little fast now, but then I can rearrange like I've done every time so far. I can rearrange and say, okay, so I've got negative omega squared times a cosine omega t plus 3.5. Well, again, just like happens like every time when this works, this whole, this whole thing here was x, right? So notice, once again, even with that extra constant term in there, once again, we do have a situation where that this cosine expression is, to answer the final question, yes, like x equals a cosine omega t plus 3.5 is also a solution to d2x dt squared equals negative omega squared x. This is very important now. Now, I'm not trying to throw anybody off, but this, and we're gonna end in 4 minutes. But what I'm even gonna go one step further before I'm saying 3.5 could have been any constant number of radians. Let this additional constant number of radians be called phi. Okay, I'm going to use the Greek letter phi, which is like a theta rotated, a 90-degree rotated pi over 2 radians, right? Phi from now on is going to be called, well, it's phi, but it's going to stand for what we're going to call from now on the phase constant. What we've just shown is that you can throw a phase constant into that cosine parenthesis. You could throw an extra little number in there. You could add it or subtract it. You could throw an extra little number in there, and it doesn't mess up the derivatives. It still allows that thing to be a solution to the differential equation. So this actually secretly gets back to something that I believe Evelyn asked like 2 days ago. What was this omega t thing, that this a cosine omega t thing that we've been churning through for 2 days now? I keep saying it's a solution to the differential equation. The thing that we now realize is, oh yes, it is the omega thing, the cosine thing that we've been talking about is a solution, but it's not the only solution. It's not the most general solution. It's a kind of specific solution. What we've been saying for 2 days is x equals a cosine omega t plus 0. What we're now saying is, you know what? We could have added any number. It didn't have to be 0. 0 was one specific easy case. We could have added any number, and we still are describing an oscillator in general. So the thing I'm going to end, so I have to talk about all the physical implications of this tomorrow. But the conclusion of this is then we have a more general solution to simple harmonic oscillation. It doesn't mean anything we've been saying is wrong. Everything we've been saying is very, very good, and it's still important for the exam and all that. But we're just now expanding and saying from now on, if D, and this is the last thing I'm going to write, and the last thing I'm going to say today, from now on, if D2, and this is the last equation that was on the first page, just so you know, you can look back now. If we see this from now on, what we can actually say to be more general is that Z will oscillate at a rate of, will oscillate cosinusoidally according to this expression. In other words, we could add any number of radians to that original omega t thing, and it will still describe our oscillator. And those of you, this is why it turns out sine works just as well as cosine, as long as you add like pi over 2 radians to the cosine to make it shift over and act like sine. I'm going to explain that more again tomorrow, but I'm just saying the inference that we draw from that exercise F of 1 of homework 2 is that, oh, actually, there's a broader set of possible solutions to the differential equation that describes harmonic oscillation, where the phase constant does not have to be 0. It could be any number of radians. We'll talk about why we would ever use that or what that means tomorrow. But that's it. So you guys, as always, are being super patient, super awesome. I'm going to pause for any questions right now, but you can go have a lovely evening. Thank you. Yes, have a wonderful night. And I'll post all this, obviously. Thank you so much. Thank you. And I'll catch up with the stuff I owe you.
Next day.
Have a great day, guys, everybody. And I'll stop the recording in a second. Thank you, guys. Okay. Have a great day. Yes, all of you. Okay, I'm gonna stop. Oh, Dante, that's Dante. Yes. Okay. Maybe you've been there the whole time. Sorry. I didn't know if maybe you've been totally showing video. That's awesome. To say bye, cat. Yes. Oh, to saying bye. Sure. Yes. Yes. Sure. Saying bye counts as closing a pathway. Sure. Yes. Fair question. Okay. I'm going to stop the recording.